Hello guys and welcome back to my channel Interview with Bunny, and today this is the 15th video of our graph playlist, and today we will be discussing a very important algorithm on graph, and that is the Kahn's algorithm. So for the last couple of videos we were discussing about the topological sort. So in our 13th video, we have discussed that what is a topological sort and what is the real life use case of the topological sort. And in our last video, we have seen how to find out the topological sort for a directed acyclic graph using the BFS approach. And in this video, we will be discussing about solving the topological sort using the BFS approach or using the Kahn's algorithm. So it can be called as the Kahn's or a Kahn's algorithm. So without wasting much time, let's get started. So if you remember in our last video when we were solving with the help of the DFS algorithm, there to solve the problem with the help of the DFS algorithm, what we were doing, we were iterating over each and every nodes of the graph. And there we were using the DFS traversal and we were trying to find out the node which is the last atomic task. Means, so for example, if this is the task for our process, we were actually trying to find out this node, that is the last node where there is no more dependent node or the dependent task to the current node. So this was our primary objective, and whenever we have found out this type of node, we were pushing it into the stack. That was the intuition or the algorithm to find out the topological sort using the DFS technique. But in the Kahn's algorithm, since we are using the concept of BFS traversal, here the way or the algorithm is a bit different. Let's see how we will do it. So the steps to solve this algorithm with the help of the Kahn's algorithm is something like this. Means we have to repeatedly remove the nodes without dependency and add them in the order. Let's understand what this algorithm is actually means. So what it actually means is like, instead of traversing all the nodes of the graph, just the way we are doing in our last video, here what we have to do, here we have to first find out the nodes with dependency. What it actually means? It means that here if you look carefully, if we consider these four are the tasks for a particular process, task T1 has a dependency of 0. Means it is an independent task and there is no task on which it is dependent. So the dependency of the task T1 is 0. Now here for the task T2, the dependency of this one is 1 because it is dependent on task T1. Similarly over here, the dependency of T3 is also 1 since it is dependent on task T1. On the same logic, if we consider that task T4 is dependent on T3, then with that logic, the dependency of T4 is 2. Means the task T4 is dependent on both T2 and T3. This is actually what we have to first find out in the Kahn's algorithm. That is the dependency map of each and every node or the vertex of the graph. That is the first objective. And if you look carefully, the dependency what we are finding over here is nothing but the number of directed edge that is heading towards. Means over here if you see, there are no edges that is heading towards T1, and that is why the dependency is 0. But here for this one, there is only one edge that is heading towards this one, and that is why the dependency is 1. Similarly over here, since there are 2 incoming edges over here, that is why the dependency is 2. This is actually what dependency map actually means. Now if you have got the concept of the first step, now let's move to the next step. So the first step was you have to find out the dependency map. Now in our next step, what we have to do, from the dependency map, we have to find out what are the independent tasks from where we can start our traversal. So here if you look carefully and if I make the dependency set over here, it will look something like this. So here you can see this is the dependency map where the dependency of T1 is 0, dependency of T2 is 1, dependency of T3 is also 1, dependency of T4 is 2, which we have already derived it from here. Now, once we have got this one, half of our job is done. Now the next step is we have to find out all the nodes where the dependency is 0. Means it is an independent process and we can start our traversal from that node. So here if you look carefully, the task T1 is an independent task because there are no tasks on which this is dependent. So according to the algorithm of the topological sort that we have learned in our last video, we should start our linear ordering from the task T1. So here we will start our traversing from T1, means this will be our topological sort ordering. So the first task that went inside the topological sort ordering is task T1. Now what will happen? Once this task is completed and it went into the ordering table, what we have to do, we have to remove all the edges that were emitting from that node. So here if you look carefully, these are the two edges that were emitting from this node T1. So we have to remove those two. Means right now these two does not exist. Means our graph will look something like this. Now what we have to do, we have to again recalculate the dependency map. So here if you recalculate the map again, you can see for the task T2, right now T2 is an independent task because there are no incoming edges. So right now the dependency of task T2 is 0. So we will change the value from 1 to 0, right? Again for the task T3, there are no incoming edges over here, means this is an independent task and we will change the value from 1 to 0. So here also we will change from 1 to 0. And for the task T4, it is still remains the same because there are two incoming edges still there. So it will remain 2 as is. We are done with this iteration. Now on the next iteration, what we'll do? Again, we will do the same thing. We will check what are the nodes or the tasks that are present with the dependency as 0. So here you can see the dependency of both T2 and T3 is 0. So we can start from any one. So what we'll do, we will start from T2 for example. So T2 will go over here. And once T2 goes over here, what we have to do, we have to remove all the outward edges, which is nothing but this one. So what we'll do, we will delete this outward edge from here. So now our graph looks something like this. So now what we'll do, we will again recalculate the dependency map. Now for the task T4, the dependency is 1. So here from 2 it got changed to 1. But for the T3, it still remains the same, that is 0. So what we'll do, as per the algorithm, we will again check which task have the dependency of 0, which is nothing but T3. So we will put the T3 over here in our ordering and we will remove the outward edge from here. So our graph will look something like this. So right now this edge is gone and we will again recalculate, and thus the dependency of T4 will become 0 right now. So here it will become 0 and again we will check which task have the dependency of 0. Here right now it is T4 and thus here we will put T4 in our topological sort ordering. And we will try to remove the outward edges. But here, since there are no outward edges associated over here, thus our algorithm stops over here. And if you look carefully, this is your topological sort ordering. That is T1, T2, T3 and T4. That's it. This is so simple. So what we are doing? We are doing two things. One, we are calculating the dependency map. And after that, we are running a loop where we are checking that which task have the dependency value as 0. And if we found the dependency value of 0, we put that task in our topological sort resultant and we will delete all the outward edges from there. And once we are done with this step, we will again recalculate the dependency tree and we will perform the same loop again. And that is how we perform the Kahn's algorithm to find out the topological sort for a directed acyclic graph. I think this is somewhat clear that how we are performing this algorithm. So now since you are familiar with the intuition of the Kahn's algorithm, now let's see systematically and programmatically that how we should perform this algorithm. So here if you look carefully, Kahn's algorithm is a modification of the BFS traversal. And since we are familiar that whenever we are implementing a BFS traversal, we need a queue data structure. So over here also to implement the Kahn's algorithm, you need a queue data structure. Now what we have to do in the next step, we have to find out the dependency map that we were talking about. So here what we'll do, we will define an array to represent the dependency map. So here since we have the nodes from 0 to 5, we will define an array of size 6. So let me define an array of size 6. And this is nothing but our dependency map. Now let's calculate the dependency of each and every node over here. So for our first node, that is the node 0, the dependency value of this node is 0 since there are no incoming edges for this node. So the first one will be 0. Now for the node 1, here you can see it have only one incoming edge. That is why the dependency of this one will be 1. So this is 1. Similarly for node 2, it will be the same thing, that is it have only one dependency. Now for the node 3, if you look carefully, there are two incoming edges over here, and that is why the dependency of node 3 will be 2. So we are writing 2 over here. Now for the node 4, it will be also 1, and for the node 5, as usual, it will be 2. So we are done with two things. One is declaring a queue and another is declaring a dependency map. Now on the next step, what we have to do, we have to start our iteration. And how we are starting the iteration? We have to first find out all the nodes whose dependency value is 0. So here if you see, for the first node, that is node 0, the dependency value is 0. So what we will do, whichever the node which have the dependency value of 0, we will push them into our queue data structure. So here, since the node 0 is having the dependency of 0, so we will put it in our queue data structure. Got it? So let me mark it over here. So here this is node 0, this is 1, 2, 3, 4 and 5. So here, since node 0 have the dependency value of 0, so we are putting it in the queue. Now what we'll do, we will start our iteration from here. Means we will pop out the element from the queue and we will print it in our resultant set. Means for example, this is our resultant set which represent our topological sort. So here in the resultant set, we are pushing the value 0 over here. Now what we are doing, since we have already popped out this element from the queue and we have printed this element, as I was telling you, what you have to do, you have to remove all the outward edges for this node. Means we will remove these two edges from here. And once we are removing these edges, the dependency map changes. Because right now for the node 1, the dependency value decreased. So for the node 1, the value of the dependency changed from 1 to 0. Similarly, for the node 2 also, the value of the dependency changed from 1 to 0. So actually removing the edges means you have to decrease the value of the neighboring dependent node by 1. So here if you see, these two were the neighboring dependent node and here we are decreasing the value by 1. This is what removing the edge actually means. So here if you see, this is our new dependency map. Now what we'll do, again we will check what are the nodes which are having the dependency value of 0, and here you can see node 1 and node 2 have the dependency value of 0. So what we will do, we will push it in the queue. So both the nodes, we will push it in the queue. So node 1 goes over here and node 2 also goes over here. Now what we'll do, we will pop out the first element from the queue, which is node 1, and we will print it in our resultant. So node 1 comes over here, and once we get node 1 over here, we will delete the outward edges from here, and thus we will change the dependency value of the neighboring node. So here the neighboring node are nothing but the node 3, so the dependency of this will decrease by 1. Similarly, the dependency of node 4 will decrease by 1, which means that we have removed these two edges from here. Now what we'll do, we'll again do the same thing and we will see the new node where the dependency value got changed to 0. So here this is the one, that is the node 4. So we will push it in the queue. So right now this is the status, that is your queue have two nodes, that is node 2 and 4. Now what we'll do, as usual right now, we will pop out the element from the queue. So node 2 comes out, we will print it over here. So node 2 is popped out, we will remove the dependency, that is this will get deleted, and the value of the dependency node, that is 3, will change from 1 to 0. So right now this is the new node whose dependency got changed to 0. So we'll push it over here. So we are done with the node 2. Now on the next step, again what we'll do, we will pop out the node 4 from here. So node 4 comes out, we will push it in our resultant and we will change the dependency map for the node 5. So what we'll do, we will make it 1. Now if you see, this dependency of node 5 is still 1. So we will not push it in the queue, right? So what we'll do, we will again check whether there is any element present on the queue or not. So here you can see we have the node 3. So we'll pop it out and we will print it and we will change the dependency tree. So here the dependent node is node 5. Thus we will change it by 1 and thus the dependency of node 5 becomes 0. And since it is 0 right now, we will push it in the queue. So right now node 5 goes into the queue. Now what we'll do, again we will pop it out from the queue, we will print it over here and we will check its dependency in edges. And here you can see there are since no edges that are going outward of the node 5, so there is nothing to modify over here in the dependency set. And thus, since right now our queue is completely empty, and thus we will stop our iteration. And thus it is the end of our Kahn's algorithm. And here if you see the resultant set, our resultant set will look something like this, means 0, 1, 2, 4, 3, 5, which is nothing but this one, which is one of our answer. And thus this is the topological sort of this directed acyclic graph. I think this is clear how we are performing the Kahn's algorithm for any directed acyclic graph. If you still have any confusion, I would highly recommend you to watch this video one more time so that you will be clear with this algorithm, because without understanding this entire logic, it will be difficult to implement. But before we start with the implementation, there is one more important thing I forgot to mention, and that is with the help of this Kahn's algorithm, we can also find out the cycle detection for a directed acyclic graph. Let me tell you how after we are done with this coding. So here you can see we have taken our online Java compiler. So let's now see how easy it is to implement the Kahn's algorithm using the Java code. So what we have done, we are using the same boilerplate code what we are doing in our complete playlist. That is, we are defining a graph class over here, which looks something like this. I hope you are familiar with this code right now. Now what we are doing in the main block, we are creating a graph object, which is nothing but the example that we were looking right now. So this is the graph class. Now what we are doing, we are calling the functionality called as Kahn's topological sort. So let's see what this function actually does, because this is the main meat of this problem. So here if I expand the Kahn's topological sort, you can see this is the complete logic and it is very easy to understand. So what we are doing, we are first declaring a integrity over here. What does integrity mean? It is nothing but the dependency set or the dependency array. So since in most of the books and in online material, this variable is mentioned as integrity, I have also mentioned the same thing over here rather than naming it as dependency map. Otherwise, you will get confused. So to keep it simple, I have also used the same convention over here. That is, I have declared an array called as integrity over here. But remember one point, the code that I'm showing over here, which is mostly available in all the online courses and the website, means whether it is Geek for Geeks, LeetCode, anywhere, you will see the same code. But all of them will fail in one condition. The condition is if the graph doesn't start with zero-based indexing, all of the code will fail, because here if you know, our array start with the zero-based indexing, and if your graph also doesn't start with a zero-based indexing, then you will get a array out of bound exception or some other null pointer exception. So keep this thing in mind. If the graph that is provided during the interview, if it is start with 0, only then you should go with this implementation. Otherwise, instead of using a integrity array, you have to go with the dependency map. Because in map means in a hash map can have any value over there and there is no zero-based indexing and your code will never fail. So remember this point. And if you want the Kahn's algorithm with the help of the hash map approach, also I will provide the same code in the description below. So do not worry about that. But right now just simply understand the logic how we are implementing over here. So here if you see what we are doing, we are defining an integrity array with the total size as the number of the vertex present over here. So here what we are doing, here we are setting up the dependency matrix or the dependency array. And how we are doing, here we are iterating over each and every nodes over here, and we are trying to find out on each and every neighboring node how many incident node or incoming node present over here, and here we are simply counting that. So at the end of this block we will get our dependency array, means it will be defined with all the dependency of the nodes. And once we are done with finding the dependency array, now what we have to do, we have to simply define a queue, since we are doing a BFS traversal over here. And in the queue, what we have to do, we have to put all the nodes where the dependency value is 0. So here you can see we are again iterating on each and every node, and we are checking whether the integrity or the dependency value is equal to 0 or not. And if it is 0, we are pushing that value in the queue. Clear? Now the next step is the iteration. So we are starting our iteration over here. And what we are doing, we are checking whether the queue is empty or not. So on the first case, since the queue is not empty, we are popping the element from the queue and we are simply pushing the result into our topological order list. And once we are done with this step, what we are doing, we have to delete all the outgoing edges from this node. So to perform that, what we are doing, we have to find out all the outgoing edges, means all the neighboring nodes for that particular node. And for all the neighboring nodes, we have to decrease the dependency. Here you can see we are just decreasing the dependency of all the neighboring nodes. Means we are removing the edges one by one. And after removing the edges, if the dependency of the neighboring nodes becomes 0, means that becomes independent, then we are again pushing that value in the queue. And that's it. This is the main fundamental logic of how to implement the Kahn's algorithm. And thus once we are done with this entire logic and once the queue is empty, you can find out the result in this topological order list. And believe me, with this Kahn's algorithm, with this simple implementation, you can at least solve 6 to 7 hard to medium LeetCode problems. So let's run this code and let's see if we are getting the expected result or not. So let me click on run and great. Here you can see we are getting the topological sorting order 012435, which we have already seen how to derive during our dry run. So I hope it is clear how we have implemented this topological sort with the help of the Kahn's algorithm. So now since you have understood that how to implement the Kahn's algorithm with the help of the Java code, let me now tell you how to detect the cycle with the help of this Kahn's algorithm. So let's understand it with the help of an example. So here let's take an example like you have 3 running tasks over here which are dependent on each other. Now here if you try to calculate the dependency map for this graph, you will find out the dependency map of all the nodes are nothing but 1. Means here there are not a single node from where we can start our iteration, because since here none of the tasks have the dependency value of 0, means no task is independent, and since there are no task is independent, so we cannot push anything in the queue, and since we are not able to push anything in the queue, our iteration will never start, and since this iteration is never starting, and that is why we can easily prove that there exists a cycle in the graph. The main intuition of this logic is like whenever you are implementing the Kahn's algorithm to any graph which is a directed acyclic graph, the total number of iteration that will happen or the total number of nodes that will get pushed in the queue should be equal to the total number of vertex present in the graph. That is the main concept, because here you are iterating over each and every node, and since you are iterating over each and every node, so it is very obvious that all the dependency value of the nodes will become zeros at some point and it will go into the queue, and thus the total number of times the iteration will happen should be equal to the total number of nodes present in the graph. And if there is a mismatch on the total number of iteration and the total number of nodes present in the graph, it means that that graph have a cycle within itself. So with this concept in mind, let's also implement this small enhancement on this Kahn's algorithm and let's see how to find out the cycle in the graph. So as we have discussed, to find out the cycle detection with the help of the Kahn's algorithm, what we have to do, we have to only keep track of the total number of times this while loop actually ran. So what we have to do, we have to simply keep a counter over here. So what we'll do, we will keep a counter set to 0. And here we will increment the counter by 1. So what we are doing on each and every iteration, whenever a node is going inside the queue, we are updating the counter over here. And here if the total number of count is equal to this number of vertex, means all the vertex wins inside the queue. And if that condition satisfies, means your graph doesn't have a cycle. But if this value differs, means all of the vertex didn't win inside the queue, means there exists a cycle. So what we will do here, we will just put a if clause that if the value of the count doesn't match with the total number of vertex present over here, means here we will print this graph is having a cycle, and that's it. This is how easy it is to detect a cycle with the help of the Kahn's algorithm. Let's also check it right now. So what we'll do, we will again create one more graph over here. So here you can see I have created the same graph that we were just discussing, the graph with the node 0, 1 and 2, and all are dependent on each other. So let's click on run and let's see and create. Here you can see this graph have a cycle over here, and I hope you are clear that how the things are working over here. So I hope you have thoroughly understood this video and you have found this video useful. And if you have found this video useful, do not forget to like, share and subscribe to my channel and hit the bell icon so that you never miss an update from my side and you are always ready for your next interview. So see you on the next video where we will be seeing how to solve the LeetCode problem with the help of this Kahn's algorithm without changing a single line of code. So see you on our next video. Thank you.